Okay, welcome to video 4 in our lecture series from Wednesday, March 8th, where we discuss Sp2 hybridization. We just discussed Sp3 hybridization, which is a result of an atom combining all of its valence orbitals, meaning it's s with all three of its p's, to form the Sp3 hybrid orbitals. And we are now going to look at Sp2 hybridization, which is different, and I'm sure you could guess based on the name, but let's get into it. So an Sp2 hybridized atom, this is an atom that has combined its valence s orbital with two of its valence p orbitals. And just for convention's sake, like I'm going to try to be self-consistent here, I'm going to call them the px and the pz. So these are the ones that are left, right, and in, out. And that combination forms what's known as the Sp2 hybrid orbitals. Now that okay, let's save that conversation for later. So again, chemists are cheap and lazy. So we called this Sp2 for a reason, and the reason was not to confuse you. In fact, it was quite the opposite. We were trying to be very straightforward with what's happening here. So in Sp2 hybridization, we are looking specifically at a combination of our valence s orbital with two of the orientations of our valence p orbitals. Here, for my sake, just to be consistent, I've chosen px and pz. And since this combination is one that involves three atomic orbitals, AO, we should expect to see three hybrid orbitals. As a result, orbitals are conserved. Okay, so here is one. Here's another. And then here's a third. We create three hybrid orbitals, all called Sp2 type orbitals. And if I want to think about how I can arrange or organize my three Sp2 orbitals such that our electrostatic repulsion is accounted for, we need to figure out how we can arrange three things such that they're as far away from one another as possible. And because they are three things, as you may have guessed, this is going to result in a triangular shape. In fact, this triangular shape is not going to be any kind of like three-dimensional triangular shape. It's not going to be a, oh gosh, some mathematician come slap me because I'm about to say trioid, like cuboid, but that's not right. Trigahedron, I don't know. The mathematicians can stop screaming. Okay, so we'll have something like this kind of equilateral triangle situation going on here. Okay, so these are our three Sp3 orbitals. And since we're talking about a triangle, you best believe that the angle between these orbitals is 120 degrees. We'll have conversations about bond angles later when we move into Vesper theory in our chemical bonding workshop. But just know that since this is a flat triangle, we call this the trigonal planar geometry. Triangular plane, flat triangle. So I'm looking at, if I were to rotate this, do something like this. Doop. Here I am showing it flat in the screen, but I could rotate it so that it was pointing in and out of the screen. All right, trigonal planar. So anytime you see Sp2, you should be thinking trigonal planar. So let's look at an example of Sp2 hybridization and why it's useful. So let's look at the compound BH3, which we actually saw as one of our Lewis structures in the first part of our chemical bonding workshop. So let's see if we can't get something that kind of makes sense or matches with what we saw in our Lewis-Dawes structure for BH3. So since we are describing a theory that thinks about what orbitals are doing, well, how about we look at the electron configuration of each of these elements? So I've got boron, and then I've got 3 hydrogens. So boron has an electron configuration of helium 2s2 2p1, and hydrogens, of course, are simply 1s1 each of them. So if I were to do a little thought experiment to see what would happen if I tried to build this without hybridization, like I tried to make the quote-unquote simplest hydrocarbon without hybridization and got something unstable in my prior video, let's see how that would work out. So we've got boron, and then I'm going to just recycle my energy axis here. So boron would have 2s and then 2p. And then I have 3 hydrogens, each with 1s. And if I'm filling in my electron configuration on each of these, boron is 2s2, 2p1, and each hydrogen is 1s1. All right, now that I've got my little orbital box diagram outlined, I am now going to search for half-filled atomic orbitals, or boxes containing only 1 electron, that could overlap such that the overlap region produces a spin-paired electron pair, the covalently shared electron pair. So I can't overlap with my 2s, right? This is already full. This leaves only that singular occupied 2p orbital open and available to create an overlap of half-filled orbitals to generate a spin pair, which is what valence bond theory calls a bond. So if I were to connect this back to what Lewis was saying, this says, oh, you have formed a sigma or single bond to hydrogen. And since we also have some kind of uninvolved 2s valence electrons, those would be indicated as a lone pair. And we see right off the bat that this is definitely something that if we were to question its stability, we would say, no way. Even though boron is an exception to octet, this is not a stable molecule. So how is it that we were able to get the Lewis structure for BH3, even though valence bond theory doesn't predict that molecule as something that can form? And the answer comes from hybridization. So with hybridization, so let's look at the hybridization process for boron, which has the 2s orbital and the 2p orbital. And we want to hybridize these. And since this is in the Sp2 section of the lecture, we are going to do an Sp2 hybridization. So let's see here, boron had 2s2, 2p1. So if I'm hybridizing to make Sp2 orbitals, then I'm going to make my S combine with 1, 2 of my P's. Overall, those new hybrids are going to be lower in energy than the P and higher in energy than the S. And since I've got 3 atomic orbitals combining, I am going to create 3 hybrid orbitals that we call my Sp2, hybridized orbitals.